This video is an introduction to the first part of Chapter 3. We'll talk about the acceleration due to gravity and motion diagrams. So we'll discuss the ideas of acceleration, the concepts, and how to interpret graphs, position versus time graphs and velocity versus time graphs, where now we have acceleration happening as well. And then we'll look at motion diagrams and how to use them. So what we talked about so far is the x component of the average velocity. Note that when we say x component, since we're dealing with only one dimension, that's what you will find. But we are specifying that there could be an x, y, or z component of the velocity or the acceleration, as it'll come up. So we discussed that the x component of the average velocity is the displacement, delta x, divided by time. And that's equal to x final minus x initial divided by t final minus t initial. If we were doing that in vector notation, we would say that was v sub x times I hat, where we've learned that I hat indicates that we're showing that the direction is along the x-axis. We also talked about instantaneous velocity, and it's worth touching on again. The definition of instantaneous velocity is basically the limit as the little time interval gets smaller and smaller, and so our little delta x intervals also get smaller and smaller, and we call that a derivative. You learn this in calculus. When you take smaller and smaller intervals, you get a derivative. We also talk about this as a slope, and when we look at this expression, Vx, or the velocity in the x direction, is equal to dx dt, that is really useful. It says that the velocity is the derivative of the position with time. You've applied this already, and will continue to do so. We also discussed how if we have a velocity versus time curve, we can do something really useful, which is discover that the area under the velocity versus time curve actually represents the displacement of the object. So you will often find it simpler, rather than using equations to sort out what the displacement is of an object, you will often find it simpler to use a velocity versus time graph to connect displacement, velocity, and time. Right, so let's move on to changing velocity. So far we've been working with constant velocity. When we have changing velocity, we now have acceleration. In other words, if an object's velocity is changing, the object is accelerating. We discussed the x component of the average acceleration of an object as the change in the x component of the velocity divided by the time interval during which this change took place. So that's a lot of words that we can simply write, still with words, as an equation. So this equation says the acceleration is equal to the change in velocity divided by the change in time. Remembering that each time we see a change word, we know that means a delta symbol. That means final minus initial, not simply velocity divided by time. It's important to check our units always, because units are the source of life, and the SI unit of acceleration is meters per second squared. So velocity is meters per second divided by time, which gives us a meters per second, or meters per second squared. We'll watch this video in class where we can see in action a changing velocity and acceleration as a cheetah hunts down its prey. So let's do a less exciting example. If we have something like a bicycle, which has an initial velocity of +8 meters per second, and it slows down to a stop, let's just find the direction of its acceleration. So I've drawn a couple of velocity vectors where the initial velocity vector is something in the positive direction, something to the right. The final velocity vector is basically 0. This is supposed to just be very small. And the acceleration is the change in velocity. The direction of the acceleration is the change in velocity. So here I've drawn x final, which is this one, v final minus v initial, which gives me the change in velocity, and this dotted line points to the left. So what's the direction of the acceleration? We expect it will be negative because we just sketched it out. And if we do it writing numbers in, we have our change in velocity equals final velocity minus initial velocity, and that's 0 meters per second minus +8 meters per second, which gives me -8 meters per second. And each time I'm writing the correct significant figures as we go through these examples. So our answer to the question is that the acceleration is in the negative axis direction, whichever way that is. Let's do another example. Suppose the x component of the velocity of a car changes from minus 10 meters per second to minus 2 meters per second in 10 seconds. The direction of the change in velocity points in the positive or negative direction. Right, so one way to think about it is to write an equation, and we can find the change in velocity, final velocity minus initial velocity, where the final velocity is minus 2 meters per second, and the initial velocity is minus 10 meters per second. So we have minus 2 minus minus 10, which gives us plus 8 meters per second. And that means that the change in velocity is in the positive direction, positive x-axis direction. Is that what we expect? Sometimes the negative signs are confusing. Negative velocity does not mean negative acceleration. We can have a change in velocity that actually indicates a positive acceleration. Next question, the x component of the car's acceleration is now positive or negative. And we know that the acceleration is change in velocity divided by time, and since change in time is always positive, the answer to this must also be positive, that the x component of the car's acceleration must be in the same direction as the change in the velocity. Right, so here's a couple of rules that if you like writing things down, this is one set of things to record. If we have an object's velocity vector and acceleration vector pointing in the same direction the object speeds up. This is a useful rule, except it can be confusing to know which direction the acceleration is. Another way to use the rule is if an object is speeding up, then the velocity vector and the acceleration vector must be pointing in the same direction. Similarly, if the velocity and the acceleration vector point in opposite directions, the object is slowing down. Right, so there's a lot of tools to help understand the concepts that you're working with and even find answers to questions and help in adding a conceptual and mathematical understanding. And one nice source is the PhETs, P-H-E-Ts, which come from the University of Colorado. And I'm going to show you a couple right now. One is called Motion in 2D or 2D Motion. And when you open it, it looks like this. If we select a linear acceleration, we start seeing our little dot moving to the right and then to the left. And you notice two arrows. Let's just show one arrow. Now, is this velocity or acceleration? It seems to always be pointing in the direction that the little red ball is moving. And now it's speeding up, velocity increasing, and then slowing down. So we can understand that this is now the velocity vector. Let's show the other vector. So this one points in the direction of the motion, and then it switches direction as the object slows down. So when the object is speeding up, points in the direction of motion, and when it slows down, points in the opposite direction. This must be the acceleration vector. And if we show both, we have the velocity vector and the acceleration vector moving in the same direction and then switching depending on if the object is speeding up or slowing down. The other PhET is pretty similar. It also gives you a bunch of options, including linear motion. This one just shows the velocity, and we can see this little ladybug slowly moving across the screen, and then it's going to turn around. There's no acceleration vector. There it is. So that was the turning around. The acceleration vector suddenly popped up, and you can see different kinds of motion. This one gets more useful when the object is moving in a circle, which we will discuss as we continue our discussion of motion. PhETs are just fun to watch. So I encourage you to open up the PhET and experiment with them. See what you can learn with each one. All right. So let's continue our discussion of acceleration by thinking about how we interpret position versus time graphs. We can get some really good information from them. We've talked about velocities so far, and now let's look at acceleration. So in these two position versus time graphs, are the velocities positive or negative? In this one here on the left, the slope is positive in the middle. It seems to be positive here, positive, 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 still positive. The change in position with some interval of time is increasing, but it's positive. The slope is positive. So the velocity is definitely positive. This graph here, the slope is again positive. But in the one on the left, the change in position is increasing with as time goes along. And in the one on the right, the change in position is decreasing as time goes on. This is going to tell us something about the acceleration. Let's look at these instead with the same set of questions. Now we have positive, our slope is now negative, so our change in position is now negative, and our velocity is therefore negative in both graphs. But what's going on with the acceleration? This one, the change in the position vector is getting longer, but it's getting longer in the negative direction. And that means that the acceleration is actually negative. While this one, the length of the position vector is getting shorter, and the acceleration is actually positive. So we have a few rules that we can that are actually quite useful. So when we have accelerating objects, the x of t curve is going to be a curve, not a straight line. In each of these cases, if the displacement increases with time, then the velocity is increasing. If the displacement increases with time, then the velocity is increasing. That's what we see in case A and not in case B. But the curvature tells us about acceleration. An upward curvature tells us that there's a positive acceleration. One way of thinking about that is that the curve lies above the tangent line. This is an upward curvature and a positive acceleration. This is a downward curvature and a negative acceleration. This one here is downward curvature, negative acceleration, upward curvature, and positive acceleration. Useful tools for interpreting position versus time graphs and knowing if your answers to the questions we are trying to find answers to are correct. So let's go on to look at acceleration due to gravity. There's a few different ways of depicting acceleration due to gravity. This is a stop motion set of photographs, or basically a set of photographs taken at equal intervals of time. And we see that the baseball, I usually use a tennis ball, the baseball is moving with greater displacement in each interval of time, which means it's moving faster as time goes on. This could actually, we have no way of knowing where time 0 is. So this could actually be a ball thrown upward and slowing down, or downward and speeding up. Here we're given an initial picture in A and a final picture in B, and we're seeing that in vacuum, two objects, a feather and a stone, fall at the same rate and both reach the bottom at the same time. And in air, the feather clearly experiences air resistance and drag, and therefore falls more slowly than the rock does. So repeating this picture again, an object falling in a straight line toward the Earth's surface is an example of accelerated motion. Really common example for us. This one that we were analyzing in the last image is the position of a falling ball, in fact, recorded at equal time intervals of 0.05 seconds. And this tells us that the speed increases and the ball accelerates. Let's plot it. If we looked at the position versus time for each of the frames in the picture, we start at 0, and then a little negative, a little more negative, more negative, more negative, and we see that we have a downward curvature, tells us our acceleration is negative, and a changing displacement with each frame. So if we plot this in terms of frames, this is position and this is change in position. Change in position seems to be more or less a straight line if we fit a line to it. And change in position is going to tell us about velocity. So this is indicating that the velocity is going from some negative value to a greater negative value. Coming back to our acceleration due to gravity for something falling, we have measured that in the absence of air resistance, the magnitude of the acceleration of all falling objects is 9.8 meters per second squared, to only two significant figures, 9.81 to three significant figures. Those are useful to memorize, but you can always look them up. And this means that the amount of time it takes to fall from a certain height is going to be the same for all falling objects in the absence of air resistance. So let's move on to how we can represent motion. And we do this with motion diagrams. They help us to write down and visualize the details of an object's motion. This example is the motion diagram for a bicycle with an initial velocity of 8 meters per second to the right, slowing down to a stop. So at our initial time, we show dots at equally spaced time intervals. This is the initial position. At the next dot, the next time interval, the dot is pretty far along. Then maybe a little bit less far, a little less far, a little less far, because the object is slowing down. So we see that the dots get closer and closer together as time goes on. This is our final time after 5.2 seconds, and the bicycle has traveled 20 meters. The final velocity is 0. We are using this to write down all the information we're given in the problem, or that we know and then that we learn as we go along. Here we know that the acceleration must be negative because it's the same direction as the change in velocity. And we could now solve for the acceleration if we wanted to do so. But we know that it's negative, so we add that to our picture. Couple more examples. This is an example of a car which is accelerating, then traveling at constant velocity. So here we've got our initial time is 0, our initial position is 0, and our initial velocity is 0. The dots are quite close together. The dots are now getting further apart, and this shows positive acceleration. The dots then are equally spaced, which shows constant acceleration, and our final velocity here is the same as some intermediate velocity, which is greater than the earlier velocities. So we've included all the relevant information, the acceleration initially, and then we could find things like the velocity after a certain amount of time and the position at the end of this travel. It would be useful, the motion diagram also helps us to see how to break up the motion into segments. So another one, let's decide what this is. So at time equals 0, position equals 0, and velocity equals 0. The dots are very close together, indicating velocity equals 0. The dots get further and further apart, indicating downward acceleration. And we notice that the direction of the x-axis has been defined as downward here. So our acceleration must be downwards. And in fact, if we include the position here as being about 300 meters downwards in the positive direction, we decide this must be a pretty big building, and it's actually example 3.2 in the text, which looks at the motion of a stone dropped from the top of the Empire State Building. Different types of graphs that you'll see, motion diagrams and kinematics graphs. This is table 3.1 from our text. It's a great reference to remember what's happening and how to represent it. This has more information than we've covered so far, but I want to emphasize the motion diagrams on the left-hand side. Something at rest, it's not moving, it's just one dot. Something moving with constant velocity is the dots are equally spaced. Something moving with constant acceleration, the dots are spaced more as time goes on. And we can also understand the position versus time graph, constant position, changing position but constant velocity, so constant slope. A curve, changing position but changing velocity, and etc. Our velocity graphs, velocity versus time graphs, and our acceleration versus time graphs, which is the new thing that we're adding. Note that in the first two cases, the acceleration is 0 because the velocity is not changing. In class, we'll make a motion diagram for throwing something up in the air and then downward, and then we'll work with that. So far we've looked at the change in velocity as things fall, and if we consider the speed of a falling object, it moves faster and faster, and the speed increases. If we define velocity as upward, then if the positive x-axis points upward, would the velocity increase or decrease? It's speeding up in the downward direction, and the velocity, however, is going to get more and more negative. So this is a tricky one. The speed is increasing, but the velocity is becoming more and more negative, which is actually a decrease. Is the x component of the acceleration positive or negative? Well, if the positive x-axis points up and the object is speeding up as it goes down, as it moves downward, then the acceleration must be in the downward direction, which would be negative. So that's a quick summary of some of the conceptual content here. Our next installment will be more equation work, but at this point we have the information to analyze motion diagrams and to understand velocity and acceleration and learn about velocity and acceleration from position versus time graphs.